How to find the preorder? Um, How to find the predecessor and successor of an element in a sorted list? The list has no duplicates. So what I mean, for example, if I have such a list 1, 2, 3, 4, 5, 6, if I choose 3, then predecessor is 2 and successor is 4. And if I chose 1, there is no predecessor, but there is a successor 2. And for 6, there is a predecessor 5, and there is no successor. So I think you understand what I want to find in this list. So actually I want to write this function which take the list and return to me, for example, let's start with the predecessor. So find predecessor. This function takes some list of elements A, some element A, and return to us the maybe element A. Okay, how can this solve this? Okay, I think the most straightforward solution is to take the elements which are less than our searchable element and take the maximum from them. And if we want to find the successor, we need to find all the maximum elements and take the minimum element from them. And let's implement this simple function, straightforward function. What if we have an empty list? No matter what we find, we can return nothing, because there is no predecessor. But what if we have some list and we have to find some element E and we need the predecessor of it? What we can do? So as I said, we can take the maximum. So we have this max function, type signature. So not actually, I want the function which take the maximum from my list, as I said. And for maximum, I think there exists some function which called maximum, which takes any foldable type and produce to us the maximum value. But here we want to take the maximum from the lowest elements. Let's call them LT, just LT. Okay, and I think this is the whole implementation. What we need to do just to define our LT, and LT is built. We can build LT from our XS. We can take the element from XS. If this element is less, E is not good element name, let's say X. If this X is less than our E, Okay. And I think the problem here is that the maximum is not total function, and I think it will fail on empty list. Yes, and I must handle this case here. So can be handled like this. I can check length of the excess. It must be greater than 0. Okay. And otherwise, we return nothing. Of course, here they return just, and here we return nothing. Let's try to load our function. So I have some error here. Actually, I don't need these guards here. I think I can remove them because I catch this here. Empty case. Let's try to compile, and we're done. So how is it? It will find it predecessor or not. Let's find predecessor for 2. You can see this is just 1 for 1. Empty list. Why we catch the empty list? So I think I need these guards. So let's check the length of LT is greater than 0. If they have some elements, we have the maximum, and otherwise we return nothing. Let's remove this pair from here to here. Let's format this like this. Okay. And now let's check for 6, for 7. This is very interesting. Why we have the predecessor for 7? Because 7, there is no 7 in this list. Okay. And for 1 we have nothing, for 2 we have 1, for 3 we have 2, for 4 we have for 5 we have 4, for 6 we have 5. And we have for 8, 6. But this is not correct result, because I don't know, can we assume that this is correct result or not? So we can define it, I think, in some ways, but I think it is better to do that if the element not in the list, then we need to say that there is no predecessor and successor. Okay. And this means that they need to check this here thing. And to check this, we have a lamp function. Yes. So if not a lamp, our E in our XS, in this case, then we can see that nothing. Yes. So if I provide the element which is not in the list, I have a nothing. But if I provide the element which is in the list, then I have the predecessor. Also, in such a way, I can do this for successor. The one thing I need to change, I need to find the great elements and select the minimum, not maximum, but minimum. Okay, but this is very simple. Okay, let's implement this. Find successor. Here we will find the elements which greater and take the minimum. From greater elements. And as you can see, they have the successors here, if they exist. Okay. Of course, this is not very fast solution because we have the sorted list and we didn't use this information to speed up our search. And we can do this by using the slightly modify the binary search. We can find their successor and predecessor in logarithmic time. So let's comment here that we have wait for forward solution. Get lower elements and extract maximum. Okay, but now let's go to solution when we can use the binary search. And I will call this function as a binary find predecessor. I think this is a nice name. Of course, we have exactly the same type signature, and I assume, assume that list sorted and no duplicates. And of course, there is a difficult case, then we have empty list, no matter what we search, we will return nothing. But what if we have not empty list and we want to find some element? So we take our binary search algorithm and we take the median of the list, and we compare our element with this median. If so, we have some cases here. If our element is greater than the median, then we can say that we must continue searching our solution from the right part of our median, and maybe the median itself our solution, but maybe not. Maybe some element from the right of the median can be our predecessor. And of course, on every step, I need to have then some element which is which can be possibly our solution, and on every step or on the iteration I need to compare the new candidate with this element, and if this candidate is greater than this previous candidate, then we have the new candidate. Okay, so let's write some code for this logic. And also I not say about other case, what if our element is less than the median? In this case, we can say that we have some solution from the left of the median. Okay. So as I say, what we need to do now, I need to compare. No, of course I need helper here. Yes, I need helper. I will call this helper with my list, and I need to define this helper. Go takes a list. And here, of course, I can move this empty case to my Go. It's better to do this. And also my Go need to have one additional argument which carry our candidate, our best candidate. So I will call it best candidate piece. So, and in the case of the empty list, we must return our base. And of course, this chart at the first point, we have no candidate, and we start our BC with nothing. The main logic is here, then we have not empty list, and I think we need some conditions here. The first condition is the median. median element must be, no, what if our element which is searching is greater than our median? In this way, we can say that our element, our predecessor, somewhere in the right part, or maybe it is the median itself. So this means that we need to run our go iteration again, but with a new candidate. We see. And of course, we need to provide the right part from the median. And here I will define this BC later. But what if our element is less than our median? Then we can say that our predecessor is somewhere from the left part of the median. Okay, because we search for predecessor, and from the right part from the median, and median itself is greater than our element, or we can say that our element is somewhere in the left part. But what we do with the best candidate here? Can our median be the new best candidate? If element is less than median, of course the median here is greater and it can be predecessor. It means that we need to stay our best candidate as it is. But here in this case we can possibly change it. Okay. And let's define this UBC here. I will define it like so we need to select the maximum from the best candidate and median. Because here our median is less than element, it can be better predecessor, so much more predecessor than the BC itself. And that's why I choose the maximum here. Okay. And then go to the right, of course, to maybe find some greater candidate. But we can have problem here because BC is maybe type and we can't use it with max function. And that's why I think I need to check this here. So I can import data maybe model. So what? And here we have some function which I think is nothing. If there is nothing, which allows us to check the value. And if our BC is nothing, then we can create a new candidate as median element, but otherwise, of course, they need to select the maximum from BC and median element. But the problem here is that I need to use a map here because maybe this can be is functional. We can partially apply our max to median element, I think, and penetrate this function to BC. Okay. And of course, here we need to return just median element. Okay. I think such a logic will work. And we have one last case. What if our element is equal to our median? In this case, we can say that our median can be our predecessor, but our predecessor is somewhere in the left, so we go to the left to do our best candidate. And we can merge these two solutions. And I think we can try to compile this thing. Of course. We can't compile because yes, I need to define my median, my left and right sublists. Of course, I will do this with split function. I already do in the previous video. So we have we can run our split at with median index and with my array. Here, and I need to better match this left and right subtrees and right subtree as a median. Yes, I think like this. And we need to define our median index. It is the length of our list divided by 2. Okay, now I think we can try to compile, and it's compiled. And let's check, should this work or not. Binary find predecessor. Please find me the predecessor in this array for element 3. We have just 2. For element 1 we have nothing. For element 6 we have 5. For element 7, 8 we have 6. And here again we have this problem if our element not in the list. should we provide a predecessor for it or not? I don't know. I don't want to write this extra logic here. But okay, let's add this logic. So I can simply add some flag here. So I have best candidate, but also I can add the flag which tells to me that find an element or not. And of course at the start I don't find it. But then later I will possibly find it. And this is my find flag. I need it here and here. My find flag. And of course I need to, so I need to extract here the extra keys, remove it from here, and if I go in this case with the element in the list, I will be in this case, and of course I need to push through because I find my element. But in any other case, I need to pass flag as it is. Okay. And in the bottom case, I need to check this flag. If we found, then they return best element. Otherwise, they return nothing. So let's try this logic. This equality here, and let's. You can see we not find our 8, but the 6 had the predecessor, and 5 had the predecessor, and 3 and 2 and 1. There is no predecessor. Also, there is no predecessor to 0 and for 100. And I think this work as expected. Have this list. Yes. Yes, it works. So, what time this takes? Of course, it takes log n time. But we use the split add function. I think this is not very good. But theoretically, this algorithm, if we do some optimization, I think it can be run with log time. Log n. The n, the number of elements in our list. But what if we want to find the successor? So this is exactly the same symmetric case, and actually I can just copy paste all this code and do some modification. So I do modification in the name of my function, of course, by binary find successor. Binary find successor. Here we need to change these two cases. What if my element is greater than median, and I want to and I search for successor? This said to me that median can be successor because it is less than element. So I don't want to do any modification here. And of course, because my element is greater than median, then the successor can be possibly in the right part of the median. And we go to that part. But what if my element is less than median? Then the median can be successor. And also the possibly best solution can be in the left side. So we need to check new best candidate here with our median and go to the left. Because we have some left part from the median, and this left part can be possibly also greater than our element, but less than our median. And in this step, of course, we need to take minimum. So if we search for successor, we take the minimum from the great elements. And I think that's all. That's all what we need. Binary find successor. For 77, they have no successor. For 6, why they and you can see they have some error here. I don't know where is it. Let's try to recompile. Yes, I think this I do some problem here. Something wrong with my logic for successor, because it actually doesn't work. For 3 it works, for 4 it doesn't work. Okay. And I think the problem possibly here in this line, what if our element is equal to our median? From which part we can possibly have the successors? Of course, we have possibility to find successor in the right part, but here I have the left part because I do copy paste. So let's reload and find successor for 4, for 3, for 2, for 1, for 6, and for 77. As you can see, all these things work correctly. Sorry, I have bad sound. I removed my microphone, so this video has the poor sound, but I don't want to rewrite it. Okay. So we have these two functions, predecessor, successor, and let's write function which find to us the predecessor and successor. So it actually gives to us the pair of maybe a. How can we do this? Of course, this is very easy with our predecessor and with our successor function. Okay, and we have the surroundings elements for any element from our list. Okay. Yes, it works as expected. Okay, but what if I want to find the predecessor and successor despite that my element is in the list or not in the list? So, for example, in the case of numbers, I want to find the closest number from the left or to the right to my number in this list if it presents. So, to do this, I need to just modify it a little bit, this code. So find predecessor despite our element in a list. So I will take this code and I need to remove this flag. So like this, I think. So I want to find predecessor anyway. Okay. I think we can try to run this. So I will now load my file. Of course, I need to rename this function a little bit. Remove this initial argument and be done. Now let's look. I want to find the predecessor in this list. For example, I have 7, 10, and now I want to find the predecessor of 8. And you can see this is 7. 8 is not in our list, but I can search for its predecessor. And for example, for 12, I found 10. But if I have 0, I have no predecessor. Okay. As you can see, this thing works. And of course, I can find the successor in such a way. I just need to do these modifications. So actually, I do my code simpler than in previous case. Okay, let's do the renaming. I'm going to see. Of course, I need to remove these flags. And now let's check for successor. 0, 1, 7, 10, 10, nothing. Okay, and let's write this function which give to us the predecessor and successor. Be a function, for example, in this list we have for example, we have some element 8 which is not in the list. I have 7 and 10 predecessor and successor. So as I said, this algorithm, in theory, will work in log n time, but in practice, in this concrete example, this not holds because we're using the list, not array, and we use this split add function, which is not very fast. But if we transfer this logic to some code which use arrays, we can use indices, and arrays can access to the elements by index by constant time, and this algorithm should work into log n time.